Surface chemistry. Surface chemistry deals with phenomena that occur at surfaces or interfaces. The interface or surface is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid dash gas or solid slash gas. Due to complete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The interface is normally a few molecules thick, but its area depends on the size of the particles of bulk phases. Many important phenomena, noticeable amongst these being corrosion, electrode processes, heterogeneous catalysis, dissolution and crystallization, occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work, and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order 10⁻⁻8 to 10⁻⁻9 Pascal, it is now possible to obtain ultra-clean surfaces of the metals. Solid materials with such clean surfaces need to be stored in vacuum, otherwise these will be covered by molecules of the major components of air, namely dioxygen and dinitrogen. In this unit, you will be studying some important features of surface chemistry such as adsorption, catalysis, and colloids, including emulsions and gels. Adsorption. There are several examples which reveal that the surface of a solid has a tendency to attract and retain the molecules of the phase with which it comes in contact. These molecules remain only at the surface and do not go deeper into the bulk. The accumulation of molecular species at the surface rather than in the bulk of solid or liquid is termed as adsorption. The molecular species or substance which concentrates or accumulates at the surface is termed adsorbate, and the materials on the surface of which the adsorption takes place is called adsorbent. Adsorption is essentially a surface phenomena. Solids, particularly its finely divided state, has large surface area, and therefore charcoal, silica gel, alumina gel, clay colloids, metals in finely divided state, etc. act as good adsorbents. Adsorption in action. If a gas like O2, H2CO, Cl2, NH3 or SO2 is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in the enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, i.e., gases are adsorbed at the surface. In a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turns colorless. The molecules of the dye thus accumulate on the surface of charcoal are adsorbed. Aqueous solution of raw sugar, when passed over beds of animal charcoal, become colorless as the coloring substances are adsorbed by the charcoal. The air becomes dry in the presence of silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above examples that solid surfaces can hold the gas or liquid molecules by virtue of adsorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent, while in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the colors of the ink due to adsorption of colored molecules, while the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from an inside. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride but adsorbed by silica gel. In other words, in adsorption, the concentration of adsorbate increases only at the surface of the adsorbent, while in absorption the concentration is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the processes. Adsorption arises due to the fact that surface particles of the adsorbent are not in the same environment as the particles inside the bulk. Inside the adsorbent, all the forces acting between the particles are mutually balanced, but on the surface the particles are not surrounded by atoms or molecules of the kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbed particles on its surface. The extent of adsorption increases with increase of surface area per unit mass of the adsorbent at given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During adsorption, there is always a decrease in residual forces of the surface, i.e., there is decrease in surface energy which appears as heat. Adsorption, therefore, is invariably an exothermic process. In other words, delta H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecules becomes restricted. This amounts to a decrease in the entropy of the gas after adsorption, i.e., delta S is negative. Adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at constant temperature and pressure, delta G must be negative, i.e., there is a decrease in Gibbs energy. On the basis of equation delta G equals to delta H minus T delta S, delta G can be negative if delta H has sufficiently high negative value as minus delta minus T delta S is positive. Thus, in adsorption process, which is spontaneous, a combination of these two factors make delta G negative. As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H becomes equal to T delta S and delta G becomes 0. At this state, equilibrium is attained. Types of adsorption. There are mainly two types of adsorption of gases on solids. If accumulation of gas on the surface of a solid occurs on account of weak van der Waals forces, the adsorption is termed as physical adsorption or physisorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, the adsorption is termed as chemical adsorption or chemisorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation and is therefore often referred to as inactivated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into chemisorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms which are held on the surface by chemisorption. Some of the important characteristics of both types of adsorption are described below. Characteristics of physisorption. 1. Lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. 2nd. Nature of adsorbate. The amount of gas adsorbed by a solid depends on the nature of gas. In general, easily liquefiable gases, i.e. with higher critical temperature, are readily adsorbed as van der Waals forces are stronger near the critical temperature. Thus, 1 gram of activated charcoal adsorbs more sulfur dioxide than methane, which is still more than 4.5 ml of dihydrogen. 3rd, reversible nature. Physical adsorption of a gas by a solid is generally reversible. Solid plus gas equilibrium, gas/solid plus heat. More of gas is adsorbed when pressure is increased as the volume of the gas decreases, Le Chatelier's principle, and the gas can be removed by decreasing pressure. Since the adsorption process is exothermic, the physical adsorption occurs readily at low temperature and decreases with increasing temperature. 4th, surface area of adsorbent. The extent of adsorption increases with increase of surface area of the adsorbent. Thus, finely divided metals and porous substances having large surface areas are good adsorbents. 5th, enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low. This is because the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristics of chemisorption. First, high specificity. Chemisorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is adsorbed on metals by virtue of oxide formation and hydrogen is adsorbed by transition metals due to hydride formation. 2. Irreversibility. As chemisorption involves compound formation, it is usually irreversible in nature. Chemisorption is also an exothermic process, but the process is very slow at low temperatures on account of high energy of activation. Like most chemical changes, adsorption often increases with rise of temperature. Physisorption of a gas adsorbed at low temperature may change into chemisorption at a high temperature. Usually, high pressure is also favorable for chemisorption. Surface area. Like physical adsorption, chemisorption also increases with increase of surface area of adsorbent. Enthalpy of adsorption. Enthalpy of chemisorption is high as it involves chemical bond formation. Adsorption isotherms. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich in 1909 gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid, adsorbent, and pressure at a particular temperature. The relationship can be expressed where x is the mass of the gas adsorbed on mass m of the adsorbent at pressure P. K and n are constants which depend on the nature of the adsorbent and the gas at particular temperature. The relationship is generally represented in form of a curve, where mass of the gas adsorbed per gram of the adsorbent is plotted against pressure. These curves indicate that at fixed pressure there is decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. Taking logarithm of equation 5.1, we get equation 5.2. The validity of Freundlich isotherm can be verified by plotting log x by m on y-axis ordinate and log p on x-axis abscissa. If it comes to be a straight line, the Freundlich isotherm is valid, otherwise not. The slope of the straight line gives the value of 1 upon n. The intercept on the y-axis gives the value of log k. Freundlich isotherm explains the behavior of adsorption in an approximate manner. The factor 1 by n can have values between 0 and 1, thus the equation 5.2 holds good over limited range of pressure. When 1 by n equals 0, x by m is constant. The adsorption is independent of pressure. When 1 by n is equals to 1, x by m equals to kp, i.e. x by m is directly proportional to p. The adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm. Thus, it fails at high pressure. Adsorption from solution phase. Solids can adsorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is adsorbed by the charcoal and the concentration of the acid decreases in the solution. Similarly, the litmus solution, when shaken with charcoal, becomes colorless. The precipitate of MgOH2 attains blue color when precipitated in presence of magnesium reagent. The color is due to the adsorption of magnesium. The following observations have been made in the case of adsorption from solution phase. The extent of adsorption decreases with an increase in temperature. The extent of adsorption increases with an increase of surface area of the adsorbent. The extent of adsorption depends on concentration of solute in solution. The extent of adsorption depends on nature of adsorbent and the adsorbate. The precise mechanism of adsorption from solution is not known. Freundlich's equation approximately describes the behavior of adsorption from solution with the difference that instead of pressure, concentration of the solution is taken into account. C is the equilibrium concentration, i.e. when adsorption is complete. On taking logarithm, we have this equation 5.4. Plotting log x by m against log c, a straight line is obtained which shows the validity of Freundlich's isotherm. This can be tested experimentally by taking solutions of different concentrations of acetic acid. Equal volumes of solutions are added to equal amounts of charcoal in different flasks. The final concentration is determined in each flask after adsorption. The difference in initial and final concentration gives the value of X. Using the above equation, validity of Freundlich isotherm can be established. Application of adsorption. The phenomena of adsorption finds a number of applications. Important ones are: 1. Production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. 2. Gas mask. Gas mask, a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in coal mines or adsorb poisonous gases. 3. Control of humidity. Silica and alumni gels are used as adsorbents for removing moisture and controlling humidity. 4th, removal of coloring matter from solutions. Animal charcoal removes colors of solution by adsorbing colored impurities. Heterogeneous catalysis. Adsorption of reactants on the solid surface of the catalysts increase the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalysts. Manufacture of ammonia using iron as a catalyst, manufacture of H2SO4 by contact process, and use of finely divided nickel in hydrogenation of oils are excellent examples of hydrogenous catalysis. Separation of inert gases. Due to the difference in degree of adsorption of gases by charcoal, a mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. In curing diseases, a number of drugs are used to kill germs by getting adsorbed on them. Froth flotation process. A low-grade sulfide ore is concentrated by separating it from silica and other earthy matter by this method using pine oil and frothing agent. Adsorption indicators. Surfaces of certain precipitates such as silver halides have the property of adsorbing some dyes like eosin, fluorescin, and thereby producing a characteristic color at the end point. Chromatographic analysis. Chromatographic analysis based on the phenomenon of adsorption finds a number of applications in analytical and industrial fields. Catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occurs in the temperature range of 653 to 873 Kelvin. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, i.e. 473 to 633 Kelvin, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of a foreign substance. The systematic study of the effect of various foreign substances on the rate of chemical reactions was first made by Berzelius in 1835. He suggested the term catalyst for such substances. Substances which accelerate the rate of chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomenon is known as catalysis. You have already studied about catalysts and its function in section 4.5. Promoters and poisons. Promoters are substances that enhance the activity of a catalyst, while poisons decrease the activity of a catalyst. For example, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. Catalysis can be broadly divided into two groups. A. Homogeneous catalysis. When the reactants and the catalyst are in the same phase, i.e. liquid or gas, the process is said to be homogeneous catalysis. The following are some examples of homogeneous catalysis. First, oxidation of sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxides of nitrogen as the catalyst in the lead chamber process. The reactants, sulfur dioxide and oxygen, and the catalyst, nitric oxide, are all in the same phase. 2. Hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. Both the reactants and the catalysts are in the same phase. Hydrolysis of sugar is catalyzed by H plus ions furnished by sulfuric acid. Both the reactants and the catalyst are in the same phase. B. Heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in the different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given below. Oxidation of sulfur dioxide into sulfur trioxide in presence of platinum. The reactant is in gaseous state while the catalyst is in solid state. 2. Combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. The reactants are in gaseous state while the catalyst is in solid state. 3. Oxidation of ammonia into nitric acid in the presence of platinum gauze in Ostwald's process. The reactants are in gaseous state while the catalyst is in solid state. 4th. Hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. One of the reactants is in liquid state and the other in gaseous state, while the catalyst is in solid state. Absorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The old theory, known as absorption theory of catalysis, was that the reactants in gaseous state or in solution are absorbed on the surface of the solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. Absorption being an exothermic process, the heat of absorption is utilized in enhancing the rate of the reaction. The catalytic action can be explained in terms of the intermediate compound formation, the theory which you have already studied in section 4.5.1. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. 1. Diffusion of reactants to the surface of the catalyst. 2. Adsorption of reactant molecules on the surface of the catalyst. 3. Occurrence of chemical reaction on catalyst surface through formation of an intermediate. 4. Desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. 5. Diffusion of reaction products away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of reaction and is effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Important features of solid catalysts. A. Activity. The activity of a catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strong onto the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by group 7 to 9 elements of the periodic table. Selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions, many products are possible. Selectivity of different catalysts for same reactants is different. For example, starting with H2 and CO and using different catalysts, we get different products. Thus, it can be inferred that the action of a catalyst is highly selective in nature. As a result, a substance which acts as catalyst in one reaction may fail to catalyze another reaction. Shape-selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of reactant product molecules is called shape-selective catalysis. Zeolites are good shape-selective catalysts because of their honeycomb-like structure. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, giving ALO-SI framework. The reactions taking place in zeolites depend upon the size and shape of reactant and product molecules as well as upon the pores and cavities of the zeolites. They are formed in nature as well as synthesized for catalytic selectivity. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in petroleum industry is ZSM-5. It converts alcohol directly into gasoline by dehydrating them to give mixture of hydrocarbons. Enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts, catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as biochemical catalysts, and the phenomenon is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. The following are some of the examples of enzyme catalyzed reactions. 1. Inversion of cane sugar. The inverted enzyme converts cane sugar into glucose and fructose. 2. Conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. 3. Conversion of starch into maltose. The diastase enzyme converts starch into maltose. 4. Conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. 5th. Decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. 6th. In stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts protein into amino acids by hydrolysis. 7. Conversion of milk into curd. It is an enzymatic reaction brought about by lactobacillus enzyme present in curd. Characteristics of enzyme catalysis. Enzyme catalysis is unique in its efficiency and high degree of specificity. The following characteristics are exhibited by enzyme catalysts. Most highly efficient. One molecule of an enzyme may transform 1 million molecules of the reactant per minute. Highly specific nature. Each enzyme is specific for a given reaction, i.e., one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. Highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature, called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. Human body temperature, being 310 Kelvin, is suited for enzyme catalyzed reactions. Highly active under optimum pH. The rate of an enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH values 5 to 7. Increasing activity in presence of activators and coenzymes. The enzymatic activity is increased in the presence of certain substances known as coenzymes. It has been observed that when a small non-protein vitamin is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na+, Mn2+, CO2+, Cu2+, etc. These metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, i.e., Na+ ions, are catalytically very active. Influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action as enzyme inhibitors in the body. Mechanism of enzyme catalysis. There are a number of cavities present on the surface of colloidal particles of enzymes. These cavities are of characteristic shape and possess active groups such as NH2, COOH, SHOH, etc. These are actually the activity centers on the surface of enzyme particles. The molecule of the reactant substrate, which have complementary shape, fit into these cavities just like a key fits into a lock. One account of the presence of active groups, an activated complex is formed, which then decomposes to yield the products. Thus, the enzyme catalyzed reaction may be considered to proceed in two steps. 1. Binding of enzyme to substrate to form an activated complex. 2. Decomposition of the activated complex to form product. Some of the important technical catalytic processes are listed in the table 5.3 to give an idea about the utility of catalysts in industry. Colloids. We have learned in Unit 2 that solutions are homogeneous systems. We also know that sand and water, when stirred, gives a suspension which slowly settles down with time. Between the two extremes of suspensions and solutions, we come across a large group of systems called colloidal dispersions or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed phase, as very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that of particle size. While in solution the constituent particles are ions or small molecules, in a colloid the dispersed phase may consist of particles of a single macromolecule, such as protein or synthetic polymer, or an aggregate of many atoms, ions, or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. Their range of diameters is between 1 and 1000 nm. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 cm size. It has a total surface area of 6 cm cube. If it were divided equally into 10 raised to the power 12 cubes, the cubes would be the size of large colloidal particles and have a total surface area of 60,000 cm square or 6 meter square. This enormous surface area leads to some special properties of colloids to be discussed later in this unit. Colloids are classified on basis of the following criteria: physical state or dispersed phase and dispersion medium, nature of interaction between dispersed phase and dispersion medium, types of particles in dispersed phase. Depending upon whether the dispersed phase and the dispersion medium are solids, liquids, or gases, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. The examples of the various types of colloids along with the typical names are listed in table 5.4. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in liquid. Firefighting foams used at emergency airplane landings are also colloidal systems. Most biological fluids are aqueous salts. Within a typical cell, proteins and nucleic acids are colloidal sized particles dispersed in an aqueous solution of ions and small molecules. Out of the various types of colloids, the most common are salts, gels, and emulsions. However, in the present unit, we shall take up the discussion of salts and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called alkosol, and so on. Depending upon the nature of interaction between the dispersed phase and the dispersion medium, colloidal salts are divided into 2 categories, namely lyophilic and lyophobic. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. Lyophilic colloids. The word lyophilic means liquid-loving. Colloidal salts directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid are called lyophilic salts. An important characteristic of these salts is that if the dispersion medium is separated from the dispersed phase, the sol can be reconstituted by simply remixing with the dispersion medium. That is why these salts are also called reversible salts. Furthermore, these salts are quite stable and cannot be easily coagulated, as discussed later. Lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, Their sulfides, etc., when simply mixed with the dispersion medium, do not form the colloidal sol. The colloidal sols can be prepared only by special methods as discussed later. Such sols are called lyophobic sols. These sols are readily precipitated or coagulated on the addition of small amounts of electrolytes by heating or by shaking, and hence are not stable. Further, only precipitated, they do not give the colloidal sol by simple addition of the dispersion medium. Hence, these sols are also called irreversible sols. Lyophobic sols need stabilizing agents for their preservation. Depending upon the type of particle of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. Multimolecular colloids. On dissolution, a large number of atoms or smaller molecules of a substance aggregate together to form species having size in the colloidal range 1 to 1000 nanometer. The species thus formed are called multimolecular colloids. For example, a gold sol may contain particles of various sizes having many atoms. Sulfur sol consists of particles containing 1000 or more S8 sulfur molecules. Macromolecular colloids. Macromolecules in a suitable solvents form solutions in which the size of the macromolecules may be in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solutions in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins, and enzymes, and those of man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. Associated colloids, micelles. There are some substances which at low concentrations behave as normal strong electrolytes, but at higher concentrations exhibit colloidal behavior due to the formation of aggregates. The aggregated particles thus formed is called micelles. These are also known as associated colloids. The formation of micelles take place only above a particular temperature called craft temperature and above a particular concentration called critical micelle concentration. On dilution, these colloids revert back to the individual ions. Surface active agents such as soaps and synthetic detergents belong to this class. For soaps, the CMC is 10⁻⁻⁴ to 10⁻⁻³ mole per liter. These colloids have both lyophilic and lyophobic parts. Micelles may contain as many as 100 molecules or more. Mechanism of micelle formation. Let us take the example of soap solutions. Soap is sodium or potassium salt of higher fatty acid and may be represented as RCOO negative Na+. Sodium stearate CH3CH216CONa, which is the major component of many soap bars. When dissolved in water, it dissociates into RCOO- and Na+ ions. The RCOO ions, however, consist two parts. A long hydrocarbon chain are also called non-polar tail, which is hydrophobic, water repelling, and a polar group CO called polar ionic head, which is hydrophilic, water loving. These RCO ions are therefore present on the surface with their CO- groups in water, and the hydrocarbon chains are staying away from it, remain at the surface. But at critical micelle concentration, the anions are pulled into the bulk of the solution and aggregate to form a spherical shape with their aggregate hydrocarbon chains pointing towards the center of the sphere, with CO part remaining outward on the surface. An aggregate thus formed is called an ionic micelle. These micelles may contain as many as 100 such ions. Similarly, in case of detergents, example sodium lauryl sulfate, the polar group is SO4 negative, along with the long hydrocarbon chain. Hence, the mechanism of micelle formation here also is same as that of soaps. Cleansing action of soaps. It has been mentioned earlier that a micelle consists of a hydrophobic hydrocarbon like central core. The cleansing action of soap is due to the fact that soap molecules form micelles around the oil droplets in such a way that hydrophobic part of the stearate ions is in the oil droplet and the hydrophilic part projects out of the grease droplet like the bristles. Since the polar group can interact with water, the oil droplets surrounded by stearate ions is now pulled into water and removed from the dirty surface. Thus, soap helps in emulsification and washing away of oils and fats. The negatively charged sheet around the globules prevent them from coming together and forming aggregates. A few important methods for the preparation of colloids are as follows. Chemical methods. Colloidal dispersions can be prepared by chemical reactions leading to formation of molecules by double decomposition, oxidation, reduction, or hydrolysis. These molecules then aggregate, leading to formation of salts. Electrical disintegration or Bredic's arc method. This process involves the dispersion as well as condensation. Colloidal salts of metals such as gold, silver, platinum, etc. can be prepared by this method. In this method, electric arc is struck between electrodes of the metal immersed in the dispersion medium. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Peptization. Peptization may be defined as the process of converting a precipitate into colloidal soil by shaking it with dispersion medium in the presence of small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. This method is applied generally to convert a freshly prepared precipitate into colloidal soil. During peptization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on precipitates, which ultimately break up into smaller particles of the size of a colloid. Colloidal solutions, when prepared, generally contain excessive amounts of electrolytes and some other soluble impurities. While the presence of traces of electrolytes is essential for the stability of the colloidal solution, larger quantities coagulated. It is therefore necessary to reduce the concentration of these soluble impurities to a requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution is carried out by the following methods. 1. Dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles in a true solution can pass through animal membrane or parchment paper or cellophane sheet but not the colloidal particles, the membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. The molecules and ions diffuse through the membrane to the outer water and pure colloidal solution is left behind. Electrodialysis. Ordinarily, the process of dialysis is quite slow. It can be made faster by applying an electric current if the dissolved substance in the impure colloidal solution is only an electrolyte. The process is then named electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment as shown. The ions present in the colloidal solution migrate out to the opposite charged electrodes. Ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filter paper can be reduced in size by impregnating with colloidal solution to stop the flow of colloidal particles. The usual collodion is a 4% solution of nitrocellulose in a mixture of alcohol and ether. An ultrafiltration paper may be prepared by soaking the filter paper in a collodion solution, hardening by formaldehyde, and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from the rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles are left on the ultrafilter paper, are then stirred with fresh dispersion medium to get a pure colloidal solution. Various properties exhibited by the colloidal solution are described below. Colligative properties. Colloidal particles being bigger aggregates, the number of particles in a colloidal solution is comparatively small as compared to a true solution. Hence, the values of colligative properties are of small order as compared to values shown by true solution of the same concentrations. Tyndall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear, and if it is observed from a direction of right angles to the direction of light beam, it appears perfectly dark. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence when viewed at right angles to the passage of light, i.e., the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. The scattering of light illuminates the path of beam in the colloidal dispersion. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. 1. The diameter of the dispersed particle is not much smaller than the wavelength of the light used, and 2. The refractive indices of the dispersed phase and the dispersion medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and true solution. Sigmondy in 1903 used Tyndall effect to set up an apparatus known as ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with the microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Ultramicroscope does not render the actual colloidal particles visible but only observe the light scattered by them. Thus, ultramicroscope does not provide any information about the size or shape of the colloidal particles. Color. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particle. The wavelength of light further depends on the size and nature of the particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed by the transmitted light. Finest gold soil is red in color. As the size of particle increases, it appears purple, then blue, and finally golden. Brownian movement. When the colloidal solutions are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of the view. This motion was first observed by the British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of the salts. Charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is same on all the particles in a given colloidal solution and may be either positive or negative. A list of some common salts with the nature of charge is given below. The charge on the salt particles is due to one or more reasons, viz. Due to electron capture by salt particles during electrodispersion of metals, due to preferential absorption of ions from solution, and or due to formulation of electrical double layer. Preferential absorption of ions is the most accepted reason. The salt particles acquire positive or negative charge by preferential absorption or of positive or negative ions. When two or more ions are present in the dispersion medium, preferential absorption of the ion common to the colloidal particles usually take place. This can be explained by taking the following examples. When silver nitrate solution is added to potassium iodide solution, the precipitated silver iodide absorbs iodide ions from the dispersion medium and negatively charged colloidal salt results. However, when Ki solution is added to AgNO3 solution, positively charged salt results due to adsorption of Ag plus ions from dispersion medium. If FeCl3 is added to excess of hot water, a positively charged salt of hydrated ferric oxide is formed due to the adsorption of Fe3 plus ions. However, when ferric chloride is added to NaOH, a negatively charged salt is obtained with adsorption of OH minus ions. Having acquired a positive or a negative charge by selective adsorption on the surface of a colloidal particle as stated above, this layer attracts counter ion from the medium, forming a second layer as shown below. The combination of the two layers of opposite charges around the colloidal particles is called Helmholtz electrical double layer. According to modern views, the first layer of ions is firmly held and is termed as fixed layer, while the second layer is mobile, which is termed as diffuse layer. Since separation of charge is the seat of potential, the charges of opposite signs of fixed and diffuse parts of the double layer results in a difference in potential between these layers. This potential difference between the fixed layer and the diffuse layer of opposite charges is called the electrokinetic potential or zeta potential. The presence of equal and similar charge on colloidal particles is largely responsible in providing stability to the colloidal solution, because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another. Electrophoresis. The existence of charge in colloidal particles is confirmed by the electrophoresis experiment. When electric potential is applied across two platinum electrodes dipping in colloidal solution, the colloidal particles move towards one or other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards the cathode, while negatively charged particles move towards anode. This can be demonstrated by the following experiment. When electrophoresis, i.e. movement of particles, is prevented by some suitable means, it is observed that dispersion medium begins to move in an electrical field. This phenomena is termed electroosmosis. Coagulation or precipitation. The stability of the lyophobic salts is due to the presence of charge in colloidal particles. If somehow the charge is removed, the particles will come nearer to each other to form aggregates and settle down under the force of gravity. The process of getting colloidal particles is called coagulation or precipitation of the salt. The coagulation of the lyophobic salts can be carried out in the following ways. By electrophoresis, the colloidal particles move towards oppositely charged electrodes, get discharged and precipitated. By mixing two oppositely charged salts. Oppositely charged salts, when mixed in almost equal proportions, neutralize their charges and get partially or completely precipitated. Mixing of hydrated ferric oxide and arsenious sulfide bring them in precipitated form. This type of coagulation is called mutual coagulation. By boiling. When a salt is boiled, the adsorbed layer is disturbed due to increased collisions with the molecules of dispersion medium. This reduces the charge in the particles and ultimately leads to settling down in form of a precipitate. By persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the salt are removed almost completely and the colloids become unstable and ultimately coagulate. By addition of electrolytes. When excess of an electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization, leading to their coagulation. The ion responsible for neutralization of charge on particle is called the coagulating ion. A negative ion causes the precipitation of positively charged salt and vice versa. It has been observed that generally, the greater the valence of the coagulating ion added, the greater is its power to cause precipitation. This is known as Hardy-Schultz rule. In the coagulation, a negative salt, the flocculating power is in order Al3 plus greater than Ba2 plus greater than Na plus. Similarly, in the coagulation of a positive salt, the flocculating power is in order of this. The minimum concentration of an electrolyte in millimeters per liter required to cause precipitation of a salt in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be the coagulating power of an ion. Coagulation of lyophilic salts. There are two factors which are responsible for the stability of lyophilic salts. These factors are the charge and solvation of the colloidal particles. When these two factors are removed, the lyophilic salts can be coagulated. This is done by 1. By adding an electrolyte, and 2. By adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic salts, the dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring about coagulation. Protection of colloids. Lyophilic salts are more stable than lyophobic salts. This is due to the fact that lyophilic colloids are extensively solvated, i.e. the colloidal particles are covered by a sheath of the liquid in which they are dispersed. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic sol is added to the lyophobic sol, the lyophilic particles form a layer around lyophobic particles and thus protect the latter from electrolytes. Lyophilic colloids are used for this purpose are called protective colloids. Emulsions. These are liquid and liquid colloidal systems, i.e. the dispersion of finely divided droplets in another liquid. If a mixture of two immiscible or partially miscible liquids is shaken, a coarse dispersion of one liquid and the other is obtained, which is called emulsion. Generally, one of the two liquids is water. There are two types of emulsions, oil dispersed in water and water dispersed in oil. In the first system, water acts as a dispersion medium. Example of this type of emulsions are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as a dispersion medium. Common examples of this type are butter and cream. Emulsions of oil and water are unstable and sometimes they separate into two layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between the suspended particles and the medium. The principal emulsion mediums for oil over water emulsions are proteins, gums, natural and synthetic soaps, etc. And for water over oil, heavy metal salts for fatty acids, long chain alcohols, lamp black, etc. Emulsions can be diluted with any amount of the dispersion medium. On the other hand, the dispersed liquid when mixed forms a separate layer. The droplets in emulsions are often negatively charged and can be precipitated by electrolytes. They also show Brownian movement and Tyndall effect. Emulsion can be broken into constituent liquids by heating, freezing, centrifuging, etc. Colloids around us. Most of the substances we come across in our life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspaper we read, and largely composed of colloids. Following are the interesting and noteworthy examples of colloids. Blue color of the sky. Dust particles along with water suspended in air scatter blue light which reaches our eyes and the sky looks blue to us. Fog, mist and rain. When large mass of air containing dust particles is cooled below its dew point, the moisture from the air condenses on the surface of these particles forming fine droplets. These droplets, being colloidal in nature, continue to flow in air and form mist or fog. Clouds are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in form of rain. Sometimes the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a soil carrying charge opposite to that one of clouds from an aeroplane. Food articles. Milk, butter, halwa, ice creams, fruit juices, etc. are all colloids in one form or the other. Blood. It is a colloidal solution of an albuminoid substance. The styptic action of an alum and ferric chloride solution is due to coagulation of blood forming a clot which stops further bleeding. Soils. Fertile soils are colloidal in nature in which humus acts as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing materials. Formation of delta. River water is a colloidal solution of clay. Sea water contains a number of electrolytes. When river water meets the seawater, the electrolytes present in seawater coagulate the colloidal solution of clay, resulting in its deposition with the formation of delta. Application of colloids. Colloids are widely used in the industry. Following are some examples. Electrical precipitation of smoke. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. in air. The smoke, before it comes out from chimney, is led through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles, on coming in contact with these plates, lose their charge and get precipitated. The particles thus settle down on the floor of the chamber. The precipitation is called Cottrell precipitator. Purification of drinking water. The water obtained from natural sources often contains suspended impurities. Alum is added to such water to coagulate the suspended impurities and make water fit for drinking purposes. Medicines. Most of the medicines are colloidal in nature. For example, argyrol is a silver sol used as an eye lotion. Colloidal antimony is used curing Kala-Azar. Colloidal gold is used for intramuscular injection. Milk of magnesia and emulsion is used for stomach disorders. Colloidal medicines are most effective because they have large surface area and are therefore easily assimilated. Tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin which contains negatively charged colloidal particles, mutual coagulation takes place. This results in the hardening of leather. This process is termed as tanning. Chromium salts are also used in place of tannin. Cleansing action of soaps and detergent. Photographic plates and films. Photographic plates or films are prepared by coating an emulsion of the light-sensitive silver bromine in gelatin over glass plates or celluloid films. Rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Industrial products, paints, ink, synthetic plastics, rubber, graphite lubricants, cement are all colloidal solutions.